Here I'm going to go through the 14th FRQ for IB FRQs. If you would like to try the problem first before you see the answers, go ahead and check in the description. There's a link to a Google document that'll have this problem. Also a link to a website with more if you're looking for more practice. If you want to try that first, then come back and look at the solution. I'm about to get going. So, in that problem you will find a chart of data, and the first question says discuss the difference between the second ionization energy and third for magnesium. So magnesium, our second is 1,445 and our third is 7,730. Just looking through, it looks like our ionization energy starts pretty low, 700, and it doubles. Then all of a sudden it goes up, 5 times as much. Then it goes up by maybe half as much of what it was, and a third of what it was, and a third of what it was, and so on. So what we're seeing is between these two there's a tremendous jump all of a sudden. So an easy way to look at this is to do Bohr models for magnesium. So that's 12 protons. We have our 1s2, our 2s2, 2p6, and our 3s2. And then start to analyze what's going on as we start to remove electrons. So if we come along and remove an electron, the first one is relatively simple. Actually, let's scale these a little bit. So the first electron we go to remove takes not too much force to remove. Not as much as an alkali metal, or a little more than an alkali metal, but what we basically have going on here is we have an effective nuclear charge of +2. So there is a lot of repulsion from these 10 electrons on these two, and they're pushing them away. And there's a very small amount in real life of repulsion between these two electrons. So there's a lot pushing this electron away, and there's more pulling it this way, but it's not terribly difficult to remove that electron. Okay. When we go to take the second one, it's going to be slightly more difficult, and the only difference is that this one is no longer there to help push that away. So now I have less pushing it away and the same amount pulling it back. And so therefore that second electron is slightly more difficult to remove, and we see that in our data. But for the third electron, let's just pick this one here. When I go to take that one away, all of a sudden it is 5 times more difficult to remove than the last one. So why is that such a big difference? And the answer lies in the fact that these 7 electrons that are in the same energy level do not do very much shielding, and in this case we're kind of considering it 0, but really there's very little shielding pushing this electron away. These 2 electrons are pushing this away, but it's 2 electrons pushing it away versus 12 protons. So in our effective nuclear charge calculation, that's simplified down, we're getting a result of +10, which means that we're seeing an increase of pull on the electrons by about 5 times as much. Okay, which then makes sense for our data. In addition, this is a little closer, so it looks like there must be something else going on a little bit there too. So when we go to the question, discuss the difference between the second ionization energy and third, we're seeing a large increase in ionization energy between the two, from 2 to 3. And that's due to the large increase in effective nuclear charge. Now, we could break that down into the proton pull and the shielding components and say that the shielding has been negated for that next energy level while our nuclear charge has remained constant. Or we could just simply leave it as an increase in effective nuclear charge. Both of answers would be sufficient to answer that question. The next question says, discuss why sulfur has a lower first ionization energy than phosphorus, and identify why that's an exception to the rule. So sulfur and phosphorus are right here. We see that the ionization energy, for the most part, is going up as we move down across the period, but all of a sudden here it drops back down. So the trend is showing us that ionization energy increases as we move right across the period. The reason why this is an exception we'll go through in a second, but to explain why ionization energy goes up across the period, that's because our effective nuclear charge is increasing as we move across the period. Or the number of protons is increasing, the shielding is not increasing as much or at all, depending on the way you're analyzing your problems. Okay. Why is this one in particular jump out? Well, for that, we actually are looking into a little bit of quantum effects. So sulfur and phosphorus, if we look at their the orbital diagrams for their valence electrons, sulfur in the 3p has 4 electrons, and phosphorus has 3. Now many people will sit there and say, oh, phosphorus has 3, it's half filled, it's stable. That is not what's going on. What's actually going on here is that the sulfur has 2 electrons in the same orbital state, and that means that they're nearby each other, and electrons repel other electrons. So what's basically happening here is that this electron is pushing on this electron away from the atom, which means if I come in and I try and pull on that, then I'm going to have some help removing that. Now these electrons are also repelling this electron, but not very much. They're not as close. This electron, on the other hand, does not have a neighbor next to it that's as close in vicinity like the sulfur does. So even though sulfur has 1 more proton, the extra repulsion from that electron is great enough to compensate and negate that extra thing, and so then phosphorus is actually a little more difficult than sulfur is to remove an electron from. So it's a pairing effect for the electrons in the same orbital that causes an extra repulsion that makes it then easier to remove that electron. Okay? The reason why that's an exception is because essentially what we're saying is that even though the effective nuclear charge goes up, we are miscalculating its shielding. The shielding actually is much higher for the sulfur final electron than for the phosphorus. Okay. Atomic radii and ionic radii for sulfur and S2-. Okay, sulfur would have 16 protons. You have your 1s2, 2s2, 2p6. And then we have 3s2, 3p4. For the S2-, let's actually switch colors here. We would have 16 protons as well. We'd have our 1s2, 2s2, 2p6. 3s2, 3p6. Okay? What we find for sulfide is that it's significantly larger in radius than the atom of sulfur. And the reason for that, effective nuclear charge based on the way we're calculating them in IB, we would have the same shielding, same number of protons. We would get the effective nuclear charge to be equal for both. Okay? It would be 16 minus 10 plus 6 effective nuclear charge. Okay, so we also have energy levels are the same. So really the only thing we have left to look for is in shielding, which we thought we had taken care of it here, but there must be more electron-electron repulsions in this that would make this bigger. So if we were to draw this, we would expect sulfide to be larger. And the explanation for that is just merely that there are more electrons. So sulfide, has more electron-electron repulsions would be the way that we would explain why sulfide is bigger than sulfur. Alright, next we're going to go through and do some chemical reactions. I'm going to go ahead and write them out. I'm going to write these out in molecular, not net ionic. So sodium metal, sodium solid, reacts with liquid bromine. That would be cool. Okay. For an alkali metal, we have something with a very low effective nuclear charge, easy to take an electron from. Halogen, we have something with a very high effective nuclear charge, good at taking electrons. There's going to be electron interchange here, and we're going to end up with an ionic compound, a salt. And I'm going to assume that that's in the solid state at that point. And then to balance, we would put 2s and 2s. No net ionic for this, there's no solution. So that would be the only way we could write that. Second one, we have bromine reacting with sodium iodide. This is probably aqueous. So bromine Br2 on the liquid state, and plus sodium iodide. Okay. So here we have something reactive, an iodide with the extra electron. This is going to take away that electron because it has one fewer energy level. We're going to end up making sodium bromide, and then iodide solid. For balancing, we would need a 2 and a 2. If you wanted to see that in a net ionic, we would do everything except for the fact that in solution, the iodide would be without the sodium ions, The sodiums are going to be spectators. The bromides would be without the sodium ions as well. They would be spectators, and we would produce iodine solid. In part C, we have iodine solid, I assume, plus lithium chloride. Iodine is not reactive enough to take an electron away from chloride, and so therefore that is going to be a no reaction. Okay, so here's your net ionic. If we wanted net ionic for this, we would do I2 solid plus Cl minus, but not really necessary given the fact that there is no reaction. Okay, part D says solid sodium oxide, so Na2O. Solid is added to distilled water. So this is going to be very relevant twice in the year, once now and once we get to acid base. Sodium oxide, a metal oxide, so sodium metal oxide, plus water is going to make a base. In this case that is 2 sodium hydroxides. And that will be dissolved in the water. If we wanted that in the net ionic form, we would write it the same way. The solid is being added, so we would not break that apart. It's not in solution. Liquid water would stay as is, but the sodium hydroxide would be ionized or dissolved in aqueous for both. Explain why the resulting solution is basic. Okay. The easy answer to that is to say you produced a base. And as you'll see in acid base, this is actually a base itself. The oxide ion is going to remove protons from things. The answer that's going to get you by safely, though, that you want to write for this is that a metal oxide plus water will be a basic solution. Okay. And that's not really an explanation. The explanation is that we're starting with a chemical capable of removing an H plus from something. But this is a sufficient explanation that you have memorized or learned this appropriate thing. Give an example of a compound that would react to form an acidic solution. We're looking for then a nonmetal oxide. So some chemicals that you might throw out would be SO2 or SO3, NO2, and NO, CO2 will form carbonic acid, P4O10. You'll notice that all of these are oxides with a nonmetal. Okay. So any of those that you knew would react to form an acidic solution. That would be it.